In the last video, we started talking about the components necessary for a nucleophilic substitution reaction. And we said that there were three main components that we needed. The alkyl group, so the carbon-based group that's attached to that halogen. We wanted to be able to tell, is it primary alkyl halide, secondary, tertiary? Is it allelic? Is it benzylic? And then we spend a fair amount of time on the leaving group. The leaving group is the halogen. So when we undergo a substitution reaction, it's that halogen that's going to be substituted, right? It's going to be leaving. And we had said that better leaving groups were weaker bases, right? Bases and nucleophiles are donating electrons. My leaving group is accepting that pair of electrons when it leaves, right? The pair of electrons that it was bonded to that alkyl group with. So weaker bases are better leaving groups. In this video, we're going to talk about our third component, and that's our nucleophile. So number 3, the nucleophile. And I had just said that bases, right, donate electrons. Nucleophiles also donate electrons. I do want to, however, differentiate between the two. So bases versus nucleophiles. Again, they both are donating electrons. It's just what they're going to donate those electrons to is going to be different. So I'm going to consider Bronsted-Lowry when I look at bases, and I'm going to say that those bases are attacking protons. Remember, the hydrogen ion, right, the proton, it doesn't have electrons. So the base is still donating those electrons. It's still supplying the electrons, but it's donating them to a proton. So I'm going to kind of combine Bronsted-Lowry and Lewis in that definition. Nucleophiles then are going to attack other electron-poor atoms, generally carbon atoms. So bases versus nucleophiles, my base, it attacks protons. Again, remember our Bronsted-Lowry definition. Bases are proton acceptors. It's accepting that proton by grabbing, right? Its electrons are grabbing onto it. So bases are going to attack protons. Nucleophiles then are going to attack other electron-poor atoms. Generally carbons. And in this case, it will be a carbon, right? It'll be the carbon that's bonded to that halogen because it's partial positive, right? The halogen's more electronegative than it, so it has a partial positive charge, making it electron poor, right? The electron density is being pulled towards that halogen. So drawing a little picture of what we're talking about here. So I'm going to bond two carbons to each other. I'm going to put a hydrogen on one of them with a couple R groups, halogen on the adjacent carbon, and let's do one hydrogen and one R group. So my base, it has its lone pair of electrons, and I'm going to have the base grab onto a proton. The electrons between that proton and the carbon would then go up to make my pi bond. My halogen would leave, and we would end up with an elimination reaction. I don't really need us to focus on that part right now. What we're really just saying is that a base is going to grab a proton. That's going to be kind of our characteristic there to differentiate between the two. My nucleophile then, also going to donate electrons, but it's going to grab onto that carbon, right? The carbon is partial positive because of that bond to my electronegative halogen. So it is electron poor, and it's going to grab onto that carbon. I want to make that arrow look more like it's pointing to carbon there. We then would lose that halogen, right? It would be my leaving group because carbon would have too many bonds. But again, really the focus right now is just that the nucleophile is grabbing onto the carbon. So my base, right, is attacking a proton. My nucleophile is attacking a different electron poor site, or something that's not a carbon. In this case, my partial positive, something that's not a proton. In this case, my partial positive carbon. So bases, protons, nucleophiles, not protons. Both of them, however, are donating electrons. So given a nucleophile slash base, how do we differentiate it, right? Is it a base? Is it a nucleophile? Would it rather attack a proton, or would it rather attack something that's not a proton but still electron poor? And often that's really hard to do, because generally, with a couple exceptions, if it's a stronger base, it's also going to be a stronger nucleophile, and vice versa. If it's a stronger nucleophile, often it's going to be a stronger base. So though a strong base is generally a strong nucleophile, we are going to have a couple exceptions where they're not the same. So first of all, they're the same when we have two nucleophiles, or two, we should say molecules, right? Because they could be bases or they could be nucleophiles. And they have the same nucleophilic atom. The stronger base is also going to be the stronger nucleophile. So for two nucleophiles with the same nucleophilic atom, so they both are nitrogens or they're both oxygens, I'm not going to compare ammonia to water. I'm going to compare something that has the same nucleophilic atom. So two nucleophiles with the same nucleophilic atom, the stronger base is also the stronger nucleophile. So again, we're talking about situations where I can't really differentiate. If I say which one's the better nucleophile, which one's the better base, it's the same answer for both of those. So the better nucleophile is the better base if I have the same nucleophilic atom. So an example of that, if I was to compare hydroxide ions, right? My nucleophilic atom in this case is my oxygen, right? It's the one with the lone pairs that it can donate. And I was to compare that to acetate. My nucleophilic atom in this case is also oxygen, right? It has the lone pairs that it can donate. So I have two different nucleophiles. Both of them have oxygen as the nucleophilic atom. And of these two, my hydroxide ion is the stronger base. I could give you pKa values, but again, we don't need them for these, right? Remember, bases want to donate electrons. My acetate has resonance. If it has resonance, it's less reactive. If it's less reactive, right, it's going to be less likely to donate those electrons. So because this, I keep making that one oxygen so much larger than the other, because it has resonance, right, those electrons are delocalized. I'm less able to donate them, right? I can still donate them, but it's not as reactive. It's stabilized. Remember, resonance stabilizes things. If it's stable, it's less reactive. So resonance stabilized. So not as reactive. Lots of so's again. So weaker base and weaker nucleophile, right? It's less likely to grab onto a proton if it's stable. It's less likely to attack a partial positive carbon if it's stable. So in this case, my hydroxide ion is both the stronger base and the stronger nucleophile. Right? Its electrons are not delocalized. Our second situation, and again, we're still talking about when nucleophilicity and basicity parallel each other, right? They're the same. So a negatively charged nucleophile is stronger than its conjugate acid. A base is a better base than its conjugate acid, right? So in this case, they're still going to parallel each other. So a negatively charged nucleophile is stronger than its conjugate acid. So we can use hydroxide again. If I was to compare hydroxide to water, right, water being the conjugate acid of hydroxide ions, right, it has one more proton. So hydroxide ions versus water. This is going to be my better nucleophile. It is my stronger base. A base will always be a stronger base than its conjugate acid. The fact that we're calling it a conjugate acid pretty much tells us that. So if I was to draw an acid-base reaction for this and said identify which one's the acid and which one's the base and which one's the conjugate acid, you're going to identify hydroxide as the base, right? A conjugate acid always has one more proton than the base. It's also my better nucleophile. One more situation where they parallel each other, right? The stronger base is also the better nucleophile. And that's as I go from right to left, not left to right, but right to left across the periodic table. So right to left across the periodic table. Basicity, which I'm spelling incorrectly, surprise there. And nucleophilicity, that's actually a word. Both increase. So if I was to compare this carbon ion, right, a carbon with a lone pair of electrons and a negative charge, right? Carbon's not very electronegative. It doesn't really like that lone pair. It wants to donate them pretty badly, right? Nitrogen, oxygen. Guess we're going to put all the lone pairs on here. And then a fluoride. As I go in this direction, stronger base. Also a better nucleophile. Again, remember both of those want to donate those electrons. Fluorine is the more electronegative of all those atoms, right? I'm comparing fluorine to oxygen to nitrogen to carbon. It can tolerate those lone pairs better, right? It's more stable on fluorine. I'm talking about donating them, so the stronger one is going to be the one where it's less stable, right? Less stable means more reactive. We want it to be reactive if it's going to be good at attacking things, right? So stronger base and better nucleophile. So what are a couple instances where they don't parallel each other, right? Where the stronger base isn't necessarily the stronger nucleophile and vice versa. So we're going to have two effects, both steric effects. So steric hindrance is going to play a factor. And then also our solvent, the type of solvent we're in, is going to matter here. So our first one, steric effects. So basicity and nucleophilicity do not parallel each other when steric hindrance becomes a factor. So basicity and nucleophilicity do not parallel each other. That's an N. when steric hindrance just means it has a lot of steric strain, right? It's hindered sterically. Becomes a factor. So remember, steric strain means I just have a lot of electron groups all kind of in each other's way, right? I think I used the personal space analogy. So it's a decrease in activity. I don't know if activity is the best word. Because I have bulky groups in the way. And I'll show you kind of what I'm talking about here. So if I was to draw out that same molecule we drew before, so I'm going to have my halogen, hydrogen, an R group, a couple R groups, and then a hydrogen, right? So remember, if we're talking about bases, I'm attacking a hydrogen. If I'm talking about a nucleophile, I'm trying to get in here and attack this carbon. And these are tetrahedral. I drew them as planar, but remember, these are sp3 hybridized carbons. They have 4 electron groups. They are tetrahedral in shape. So steric hindrance, if I have a lot of big bulky groups, steric hindrance is going to decrease nucleophilicity, but not basicity. And I will show you on that picture there in a second, but let's write this down. So steric hindrance decreases nucleophilicity. See if we can fit it here. Kind of. That says nucleophilicity, but not basicity. Let's squish that so it actually looks right. Nucleophilicity. It's a hard enough word to say. I want to make sure that it's spelled correctly for you. So steric hindrance is going to decrease nucleophilicity. So if you have a lot of steric hindrance, it's not going to be a very good nucleophile, but it can still be a good base. So steric hindrance decreases the ability to be a nucleophile, but it's not decreasing its ability to be a base. So our example, let's say that my nucleophile, we'll do 2 of them. Let's compare this. So this is ethoxide. You don't need to know the name, but I'm going to refer to them by name because I'm not going to say the zigzag line with the oxygen. So ethoxide. And then we'll do T-butoxide or tert butoxide. So I have a tert butyl group, and then it's bonded to that oxygen. And I'm drawing these as skeletal structures, but remember, like if I was to draw out that T-butoxide, I'll write down the name here in a second, right? That's going to a carbon, and then that carbon has 3 hydrogen on it. And then that's going to a carbon, and that carbon has 3 hydrogen on it. And then that's going to a carbon, right? And then that carbon has 3 hydrogen on it. There's a lot of steric stuff going on here, right? There's a lot of groups. That's pretty big and bulky. And sometimes it's easy to forget about that when we draw skeletal structures, but that's a lot going on. So that, I would say, has some steric strain when it tries to get in there to attack. So this is T or tert butoxide, right? It's a T-butyl group, but it has an oxygen with a negative charge. So T-butoxide. So if T-butoxide was my nucleophile, right? It has to try to fit, and let's use, this is going to be a crazy arrow. We'll try to fit it on the, I'm going to make this a little bit smaller here. It has to fit in here, right? And that R group Let's draw that out. If I just wanted to do a methyl group, but it could be an ethyl group, it could be a T-butyl group, right? It has some hydrogens on it. There could be an R group here. It's hard to fit in there, right? It's not planar like this. I have a bond coming out at us if I was to draw it correctly. I have a bond going back. And T-butoxide is just too big and bulky to fit in there and grab that carbon. It just doesn't fit. However, if it's going to act like a base, it doesn't have to fit in there, right? If it's going to do a base thing and grab a proton, it can grab this, which is hanging off the side. So to try to fit into that carbon, right? Remember, it is tetrahedral. So I would have, even if we just do a methyl group, right? I got a hydrogen, I got another hydrogen. Here I have a hydrogen, I have my halogen, I have this carbon with all of its groups on it. Right? It doesn't fit in there. There's just too much going on. I got this thing coming out at me. It just plain can't fit. There's just not enough room. So if my nucleophile slash base is big and bulky, it's going to be a better base than it is going to be a nucleophile. It just can't fit in there and grab onto that carbon because the carbon's buried, right? It's got all that stuff coming off of it. This hydrogen is just hanging off the end, so we can grab onto that. So let's put some of that into words. So, oops. Let's make it back to the normal size here. So, bulky nucleophiles can't fit, right, very well. Right? They need to attack that carbon. So they're just not fitting in there. But can grab the proton, right? The proton's not buried in there, it's hanging out the end. So because it can't get the carbon, it's not a very good nucleophile. Because it can still get the proton, it is a good base. So my T-butoxide here is going to be a stronger base, but a weaker nucleophile. Stronger base, weaker nucleophile, right? Too much steric strain, right? It's sterically hindered. It doesn't fit. My proton is hanging off the end, so we can still go grab that. So one of the factors, right, where nucleophilicity does not parallel basicity is if I have steric factors, right? If it can't fit into that carbon, it can still grab the proton off that's hanging off the end. So bulky nucleophiles that can't fit in there very well, right? But they can still grab that proton. So stronger base, but weaker nucleophile. They're not paralleling each other anymore. The second situation where nucleophilicity and basicity do not necessarily parallel each other has to do with the size of the nucleophile and my solvent. So nucleophile size and solvent effects. So most organic reactions do occur in a liquid solvent. Because my alkyl halide is polar, we're going to use a polar solvent, right? The whole like dissolves like thing. So most organic reactions do take place in a liquid solvent. Because my alkyl halide is polar, polar solvents are used, right? Like dissolves like. If they have similar polarities, they tend to form solutions. So my alkyl halide is polar. So polar solvents are used. And there's two types of polar solvents, polar protic solvents and then polar aprotic solvents. So before we get into the details about how this affects nucleophilicity and basicity, I want to spend just a little bit of time talking about the two types of solvents. So we'll do polar protic solvents first. And polar protic solvents are going to be solvents that are capable of hydrogen bonding. So they're going to contain, this is how we're going to recognize them, an oxygen-hydrogen bond or a nitrogen-hydrogen bond. Remember fluorine-hydrogen bonds, those can also form fluorine-hydrogen bonds can also form hydrogen bonds. It's kind of weird to say, but we're not going to see hydrofluoric acid as a solvent, so I'm just leaving it off the list. If I give you a solvent and we're trying to decide, is it polar protic or polar aprotic? Does it contain an OH bond? Does it contain an NH bond? If it does, it's going to be a polar protic solvent. It is capable of hydrogen bonding. And what that means for us is that it can solvate both cations, so our positively charged ions, and anions, our negatively charged ions well. Solvate, if you're not familiar with that term, it just means that the solvent molecules are surrounding and forming intermolecular forces with the ion or whatever it is that it's solvating. Solvation tends to stabilize it, right? If I have intermolecular forces with other molecules, it's a stabilizing effect. So we could say that polar protic solvents tend to stabilize both cations and anions well. We could draw a little example here. If I had sodium ion, so I have a positive charge, and then let's use water as our solvent. The oxygen end of water is my partial negative end. So I'm going to orient the partial negative towards my positive, right? I would have an ion dipole force, right? This is partial negative, partial positive. And those partial negatives are going to be attracted to my positive sodium ion. So we could draw intermolecular forces, in this case ion dipole forces, between the sodium and my solvent, specifically the oxygen end of my solvent. We could use bromide ions, so Br minus as a negative charge, so this is an anion. This time I'm going to orient the hydrogen end of the water molecule towards the bromine. And I also have ion dipole forces. I'm going to show hydrogen bonds, but I do also have ion dipole forces, right? The hydrogen's partial positive, that's going to be attracted to the negative bromide ion. But I do have lone pairs on here. And I know this isn't typically how we described hydrogen bonds, but we are going to consider them as such. So I'm drawing connections between the hydrogen that's attached to that oxygen and the lone pair on my bromine. So I have both a cation and an anion that are being stabilized by that solvent. If I have polar protic solvents, nucleophilicity is going to increase down the group as the size of the anion increases. This is going to be the opposite to basicity, and we'll write that down here. So in polar protic solvents, again, we're going to recognize those by seeing that they have an OH or an NH bond. So in polar protic solvents, nucleophilicity increases down a group as the size of the anion increases. So if I was to look at fluoride versus chloride versus bromide versus iodide, right? We know from the past that as I go in this direction, right, it's a stronger base, right? We talked about this in the previous video. Fluoride, right? Fluoride ions, it's the conjugate of a weak acid, right? Makes it a stronger base. We knew that chloride, bromide, and iod ions are inert, right? They're the conjugates of strong acids. Essentially, they're more polarizable. They can stabilize that extra lone pair and that negative charge better. Fluoride is not as big, it's not as polarizable, it can't stabilize them as well. So it wants to donate them, while chloride, bromide, and iodide are okay to keep them. So as I go up, it's actually going to be a stronger base. However, as I go down, it's getting larger. And we just said that if we have a polar protic solvent, my nucleophilicity is going to increase as the size of my anion increases. And this is only in polar protic solvents. So I'm going to have a better nucleophile a reason for that is a bigger, and I'll talk about this here in a second, bigger anion, basically bigger atom. If you want to think about it that way, it still works. It's just a charged atom. So better nucleophile in polar protic solvents. Again, that part's important. So one of the places, right, where nucleophilicity and basicity do not parallel each other is in a polar protic solvent, right? If I had water, fluoride ions would be the stronger base, but the weaker nucleophile. The reason for that is the whole solvation. Remember, we just said that solvating something stabilizes it. Remember, nucleophiles and bases need to be able to attack something. So if I am stabilizing my nucleophile with solvation, it's going to be less reactive. The bigger it is, the less we can think about it as being hidden, right? Fluoride's really small, so the solvent surrounds it really easily and kind of hides it. It's super stabilized, where iodine is much larger, so it's not as hidden. Maybe it's easier to think about it that way. So fluoride is well solvated. So less likely to react. With the alkyl halide, right? It's stabilized by the solvent. Iodide is big, not as electronegative, not as well solvated. Right? Not as hidden. Right? It's not quite as surrounded by that solvent. My polar aprotic solvents These are not going to be capable of hydrogen bonding. They're not going to contain an OH or an NH bond. So do not contain an OH or NH bond. So not capable of hydrogen bonding. These are only going to stabilize cations well. So only solvate. The cations are not my base or my nucleophile, right? It's the anion. So the one that's electron rich. So these are not going to stabilize my nucleophile or my base as well. So again, if I was to look at sodium, and then we'll use acetone. Acetone's a ketone. It has this structure as my solvent. I do have an oxygen that's partial negative, right? It's more electronegative than that carbon is. So I can still form pretty decent ion dipole interactions with that cation. However, if I was to look at bromide, though that carbon is partial positive, I just made bromide kind of weird. Even though that carbon is partial positive, it's the ion dipole interaction between that and bromine just isn't really that strong. And I don't have hydrogen bonds, right? I do have carbons that are bonded to hydrogens, but I don't have hydrogens bonded to oxygens or nitrogens. So I'm not going to draw any connections this time, right? Those connections representing my intermolecular forces. So I drew some dotted lines over on my cation, but I'm not going to draw them on bromide. Again, I do have some ion dipole forces, but they're pretty weak. It just, when I say well, I'm not saying, that it doesn't stabilize or solvate anions. It's just not doing a really good job of it. So the only one that it does a really good job of solvating are my cations. Some examples, because you do have to be able to recognize, if I give you a set of reaction conditions, you need to be able to tell, is it protic or is it aprotic? Because we want to be able to differentiate, is it going to be a strong base? Is it going to be a strong nucleophile? Is it going to be good at both of them? So there are some tables in your book. Again, this is only coming from the 5th edition, so it might be slightly different, but figure 7.7 in your text. This lists some polar aprotic solvents. The protic ones tend to be easier to recognize because you're looking for that OH or NH bond. And this is by no means an inclusive list. Like there's others, but these are just some common ones. And I'll write them here. So acetone, sometimes I'll draw the structure, sometimes I'll write the word, so do know both of them. This one I'll rarely write. I'll usually give you initials, but this is THF. It's tetrahydrofuran would be the whole name. I don't care that you know that, just know THF. A lot of the polar aprotic solvents are actually going to be some initials, so DMSO. Again, it's an acronym. It stands for dimethyl sulfoxide. Again, I don't care that you know that, but if I write down DMSO, know what it is. So dimethyl sulfoxide, that's what that is. DMF is another one. This one is dimethylphosphoramide. It's big. I'm not going to draw it, but it doesn't have an amide functional group. I say I'm not going to draw it, and then I do it anyway. So remember the amide functional group, I have a carbonyl bonded to a nitrogen, and then the DM stands for dimethyl, so that nitrogen is then bonded to 2 methyl groups. We're still under HMPA. Like I said, most of them you're going to see acronyms. This stands for hexamethylphosphoramide. Again, just recognize that the HMPA as being aprotic. These are polar aprotic. Another one that's not on this list that I use a lot is just diethyl ether. So diethyl ether. Sometimes they'll just say ether. We know ether is an entire functional group, but just if you say ether, if someone's talking about ether outside of a chemistry class, they're probably talking about diethyl ether. So a lot of times we'll just say ether if I put that on the line. So if I give you one of these, it's going to be a polar aprotic solvent. Again, there's others, but this is a list of fairly common ones. Protic ones, these are going to be pretty obvious, I think. Again, they have to have that NH or OH bond. So water, an alcohol, we could do an amine. Those are going to have polar bonds in them, right? Sorry, hydrogen bonding capabilities. So NH2 with an R group on it. Acetic acid is another one. Be able to recognize acetic acid if it's drawn out or if it's written. So acetic acid, the way you would have probably written it in general chemistry, as a 3, sorry. Something like that. So CH3CO2, sometimes CH3COO, it's written out. I have seen it as C2H3O2. I usually don't combine those, but just be able to recognize acetic acid in all of its different forms. So if I gave us an example, and I said, which is the better nucleophile? And then I gave us a couple examples. So we'll do CH3S minus versus CH3O minus, and we'll do it in water. Which one are we going to pick? So the first thing I'm going to think, okay, water, does that matter? Well, water is going to be a protic solvent. So because water is a protic solvent, it is going to matter. Polar protic. So for this one, I know that the one that has the larger atom is going to be the better nucleophile. So if you look at your periodic table, sulfur is a larger atom than oxygen. So this is going to be my better nucleophile. If I said in acetone, I'm actually going to pick the other answer because the CH3O minus is a stronger base. And I know if I'm not in a protic solvent, then the stronger base is the stronger nucleophile. So do pay attention to, if it gives you a solvent, what that solvent is, because it is going to have an effect on our answer.